Okay, so we've looked at examples for average gradient, for instantaneous gradient, now an example of the derivative. Okay, find the derivative from first principles for the following function. Okay, now again remember, first principles is a more complex way. There is a very simple way to find the derivative, extremely simple. Okay, but we're not there yet. For now, we take the long way around. Okay, and that is from first principles using this formula. The derivative is found by taking the limit of h tending to 0 of fx plus h minus f of x when divided by h. Okay, now it is important to note that that the derivative, that's this thing here, is a formula for the gradient. A formula for the gradient. Okay, gradient, remember, is the steepness. Well, loosely defined, it's steepness. Okay, so if I draw this graph, which would look something like that, okay, something like this, then at different points on here we will have different gradients. Okay, so for example, at that point the gradient will be different than at, let's say, this point. Okay, so see, there's that gradient, where this gradient is slightly less steep, both downhill but slightly less steep. So it depends on what x value I'm at, that x value or that x value. So for different x values we get different steepnesses or gradients. So the derivative is a formula, so that all I need to do with that formula is substitute in the x and I find the steepness at that point. So it's also a function. Okay, it's a formula or a function. Okay, and we find it by solving this without replacing x. We keep x just x, so that when we want to find the derivative at a point, in other words the instantaneous gradient at a certain point, we substitute into the derivative formula that we get. So let's see. So I get that the limit of h tending to 0 of fx plus h. Now x plus h is the input, and what does f do to the input? Well, it does two things. It cubes it and then multiplies it with -3. So the input is x plus h. That must be cubed and then multiplied with -3 minus f of x. Now the input is just that, so -3x cubed. That's what fx is. We divide this by h. Am I allowed to substitute? Of course not. H equal to 0 will make my denominator equal to 0, so I'm not allowed to substitute. So I first have to simplify. Okay, so we have the limit of h tending to 0, which I must write until I get to substitute. Okay, in the numerator, this is what I get, -3. Now I know a short way of multiplying this out. You're going to do the long way. x3, I've done it so many times, I know what is, plus 6x 3x squared h plus 3xh squared plus h cubed. Okay, so how did I get that? Well, you have three brackets that you multiply out, x plus h, x plus h, x plus h. Multiply out the first one, you get x squared plus 2xh plus h squared, and then everything in here has to be multiplied with an x and with a plus h. And when you do that, this is what you get. And I'm not going to show you the short method because I want you to go and practice this enough so that you can even remember it. Okay, so plus 3x cubed. Okay, now you'll see that 3x cubed, this last term will always cancel with the first term in here. Okay, if you did it correctly, and in this order, that would be your first term. Okay, so that now we see the -3 gets multiplied in, so I get -3x squared plus, x cubed plus 3x cubed, and that just cancels. So I'm left in my next step with So if I multiply in the 3 with the rest of the terms, I get negative 3 times 3x squared gives me negative 9x squared h. Negative 3 times 3xh squared gives me negative 9xh squared. And negative 3 times the last term gives me negative 3h cubed. Okay, first terms have cancelled and my denominator is still just h. Now you'll see if you've done this correctly, then your first term, the one that does not include the h, will cancel with the second, well, the last term in this case, which was which is this part. They will always cancel, and what we are left with is actually every term in the numerator with an h. Now that's brilliant because that allows us to take out h as a common factor. So let's do that. If I take out h as a common factor, I get h negative 9x squared minus 9x h minus 3h squared. Okay, so you see if I multiply this h back, I'll get the same thing that I had up there, divided by h. And this is perfect because we could take out an h as a common factor. It can now cancel with the h in the denominator, which is what we've wanted all the time, because I don't want to substitute h with 0, because that would make my denominator 0, something that's not allowed to happen. But now we see that we don't have a denominator anymore, which means that I'm welcome to substitute h with anything I want to. In this case, it has to be 0 though. Okay, and that's even better because that makes this 9x times 0, so this will just cancel, and 0 squared is just 0, so that will also just cancel. So when I do substitute, my answer is simply negative 9x squared. Notice I've left out the limit now because I've done my substitution step. Then I can leave out the limit, and this is it. The derivative of fx, if fx is equal to negative 3x cubed, the derivative is negative 9x squared. In other words, this is a formula for the gradient at any point. So now you ask me, okay, so what is the gradient when x is equal to 1? Then I'll substitute and I'll say, well, the derivative when x is equal to 1 is equal to negative 9 times 1 squared, which is just negative 9. So when x is equal to 1, that's somewhere there, okay, this gradient is negative. You can see it's going downhill, so it's negative 9. Okay, that is the steepness of this line if someone was to walk on it. Okay, that is it for me for now. And I'll see you in the next video. I think we'll probably do another one of these examples, but where the function that I have is actually a fractional function, in other words, or a hyperbola function, let's say that.